Hello, class. Today we are going to dive into the first part of a two-part lesson on atoms, molecules, and ions. The bulk of this lesson will be focused on atomic structure and the parts of the atom, but we are also going to look at some fundamental chemical laws that will serve as the backbone for the second part of this lesson, which is formula writing and compound formation. So when we look at chemical writing and chemical nomenclature and things of those matters, we need to be able to understand why these compounds are forming. So we're going to look at these three ideas here. The law of conservation of mass, which we've mentioned previously. It's this idea that mass is neither created nor destroyed. This primarily pertains to chemical reactions, especially balanced chemical equations, and the need to balance chemical equations. But it also tells us that we have compounds that can break apart in the course of a chemical reaction and then reform new compounds. As a result of these changes from reactants to products, we will see that the mass stays constant. As a result of these things, scientists were able to measure the masses of elements within compounds and came up with these two laws, the law of definite proportions and the law of multiple proportions. The law of definite proportions says a given compound always contains exactly the same proportions of elements by mass. So, for instance, CO2, which we'll talk about in a minute, always has 32 grams of oxygen and 12 grams of carbon for a total mass of 44 grams. That proportion, those percent compositions, are always going to stay the same. We're going to look at percent composition later on in a different lesson, but this is the backbone of that idea. An application of this is also the law of multiple proportions, which says when two elements combine to form a series of compounds, the ratios of the masses of the second element that combined with 1 gram of the first element can always be reduced to small whole numbers. Essentially, these two laws, in tandem with the law of conservation of mass, just says that compounds are going to form in specific defined ratios. So we're always going to have a certain amount of atoms of a particular type within a compound. And we're going to look at some of those rules as time unfolds. So this all started with a famous chemist named Dalton. We're going to look at his atomic theory briefly. But in one of his experiments, he took 1 gram of carbon and determined the mass of oxygen associated with that 1 gram of carbon. And he looked at two different compounds. And he saw that in compound 1, he had 1.33 grams of oxygen for every 1 gram of carbon. And he had 2.66 grams of oxygen in the second compound. If you're looking at that ratio here, if we divide by 1.33, it can be assumed that for every 1 carbon, we have 1 oxygen. If you divide 2.66 by 1.33, that tells you have 2 oxygens for every 1 carbon. So he was able to hypothesize and come up with the possible identity for compound 1, saying that it was carbon monoxide, CO, and a possible identity for compound 2 was CO2, carbon dioxide. If you try the same thing in exercise 1, if we take the smallest mass and divide the others by that mass, we can come up with a ratio for how much nitrogen is bonded to each of these oxygens. So we're starting with 1 gram of oxygen, and all the reported masses here are masses of nitrogen. So the smallest one is the 4375 grams. 0.4375 grams. 0.4375 grams. Okay. The first one, quite obviously, is going to be much larger, so we'll save that one for last. But when we divide something by itself, that means we have one of that number. So we have 1 nitrogen in compound 3 combined with 1 oxygen. If we check our math for the other ones, and I'll pull up my calculator here. So 1.75 divided by 0.4375 tells us that we have 4 nitrogens for 1 oxygen. And then if I do 0.8750 divided by 0.4375, I have 2 nitrogens for that oxygen. So since this tells us we have 2 and 4, quite possibly these could be identities of the compounds that we are looking at here. This is a perfect illustration of the law of multiple proportions. This idea of dividing by the smallest mass or by the smallest amount to determine the subscripts in a formula is something that's going to come into play in our next unit when we look more at stoichiometry. We're going to look at something called the empirical formula and the molecular formula. So this idea is important, and we'll come back. When looking at Dalton's atomic theory of matter, there were 4 main postulates, and there have been some modifications since then. So the first postulate, all matter is made of atoms. These are indivisible and indestructible objects, and they are the ultimate chemical particles. Obviously, we know now that there are subatomic particles, such as protons, neutrons, and electrons. So atoms are still not the smallest part, but they're the smallest workable part that retain their characteristics. All the atoms of a given element are identical in both weight and chemical properties. However, atoms of different elements have different weights and different chemical properties. This second postulate is mostly true, but you have to keep in mind now that we know about isotopes, which are things that have the same protons but different number of neutrons and therefore different mass. They have the same identity, but they're slightly different in mass, and as a result, when we take the average of all of the isotopes, we come up with the average atomic mass. So number 2 is roughly true, but we'll have to keep in mind average atomic mass, which we'll talk about more in our next lessons. Compounds are formed by the combination of different atoms in the ratio of small whole numbers. So that actually is just the application of the law of definite and law of multiple proportions. And then a chemical reaction involves only the combination, separation, or rearrangement of atoms. Atoms are neither created nor destroyed in the course of ordinary chemical reactions. And that is also an application of the law of conservation of mass. So within Dalton's atomic theory, he incorporated some of the fundamental laws that we just talked about. And that's why it's important that we led the topic with those, because they are going to remain relevant in our discussion here. There were some additional scientists doing work at the same time. Avogadro is one of them. If you've taken a first-year chemistry course, then Avogadro, is famous for the mole, but he also was famous for some work dealing with gases, specifically the amount of gases and the volume of gases when temperature and pressure is held constant. When we dive into gas laws, you will see this hypothesis come up again. It's referred to as Avogadro's law. But it's this idea that at the same temperature and pressure, equal volumes of different gases contain the same number of particles. That's where the conversion 1 mole of gas is equal to 22.4 liters at standard temperature and pressure comes from. That is something you will want to memorize, that conversion. It will be helpful for you later on. Again, I just threw it in here because it was related to the same experiments that were being conducted around the same time as Dalton. When we're talking about the modern view of atomic structure, we're going to start by looking at elements. We know that all matter composed of only one type of atom is an element. There are 92 naturally occurring elements. The rest are man-made. We're actually up to 118 elements at the point of recording of this video. The most recent one, I believe, was named in 2018, and that is element 118, and that is oganesson. There are a lot of studies going on right now using particle colliders, such as the Large Hadron Collider in Switzerland, where they basically smash really heavy nuclei together in fusion reactions in an attempt to create additional elements. So when we say they're man-made, that's what we're referring to. The picture on the right is really important because it actually shows how small the nucleus is compared to its electron cloud. And as a result, the atom is mostly empty space. We have a dense nucleus that contains the protons and neutrons, and that's where the bulk of the mass is. But the electron cloud for that atom is much, much larger. And you can see the factors here, 10 to the negative 8th compared to 10 to the negative 13th in diameter. So the electron cloud is a couple thousand times more in size compared to the nucleus. The atom is the smallest particle of an element that retains the chemical properties of that element. As we just discussed the nucleus, it contains our protons and electrons. The electrons are outside the nucleus. They do not orbit the nucleus. We're going to talk about atomic theory a little bit more when we're looking at electron configurations and quantized energy levels and things of that nature, but that's for another time. So if you're used to the Bohr model idea with electrons orbiting the nucleus in fixed rings and things like that, that is not true. We now go with what's called the quantum mechanical model, which just allows us to define electrons as moving within orbitals, which are probabilities based off of wave functions and some multivariable calculus. Okay, so the proton we know has positive charge. It's responsible for the identity of the element, and that is our atomic number. So if I'm looking at the periodic table here, the atomic number is up top, and that is unique to each element. Each element has a unique number of protons and therefore atomic number. If you change the protons, you've changed the element. For neutrons, neutrons have no charge. They're about the same size and mass as a proton, and they're responsible for giving us isotopes because it alters our mass number. Mass number, as we'll talk about in a minute, is related to the protons and neutrons. It is different from average atomic mass. Average atomic mass we'll talk about later on, but average atomic mass is based off of all of the possible isotopes, whereas mass number is specific to one kind of isotope. Electrons have a negative charge, the same size as a proton or neutron, but 1/2000th the mass of a proton or neutron. So essentially, we do not count the electrons in the mass of our atom because it's so small in comparison, despite being the same size. These are responsible for bonding, reactions, and ionizations, and they can also be easily added or removed, as we'll discuss when we get into chemical reactions. Okay. Some notation stuff. If you see P plus, that refers to proton. N with O as a superscript, that is a neutron. And then E with a minus refers to an electron. This table here just shows you the relative masses. So you see the masses are relatively the same. They're very close for protons and neutrons, and then the electron is much smaller. As I stated before, the atomic number, which we sometimes refer to as Z when we're looking at isotope symbols, is the number of protons in the atom, and it's unique to that element. We also have the mass number, which is the sum of the neutrons and protons for an atom. Different mass number does not mean a different element, just different isotope. And as I said before, it's not the same as average atomic mass. This format that we're going to use here for mass number and atomic number, we write this when we're writing notation for specific isotopes. This is going to look different from the periodic table, especially because the atomic number is on the bottom and you're used to atomic numbers being on the top. And then the mass number is on the top when you're used to average atomic masses on the bottom. Again, you're not going to use average atomic masses when writing isotope symbols. So isotopes are atoms that have the same number of protons, but different number of neutrons. Most elements have at least two stable isotopes, and there are only a few that exist with only one stable isotope. You don't need to know which ones those are, but just interesting to point out. When we name isotopes, we write the element name, a dash, and then the mass number. So if we're looking at the tritium isotope of hydrogen, it has 2 neutrons and 1 proton for a total mass of 3. So we write it as hydrogen 3. Now these names that I've put here related to hydrogen's isotopes are an old nomenclature that has just been used consistently throughout time. Hydrogen with 1 neutron is referred to as deuterium, and 2 neutrons is referred to as tritium. But if you were to name it as hydrogen 3 or hydrogen 2, that would equally be acceptable. So again, here's our nucleus. Remember, the nucleus is dense, has all of the mass with protons and neutrons, and the electrons are in a cloud on the outside. And you can see here with these 2 sodium isotopes that we're looking at, they both have 11 protons, making them sodium, but they have a different number of neutrons. We go from 12 to 13. Since that mass changes due to the neutrons changing, you'll see the number goes from 23 to 24. So let's put that into practice. Write the symbol for the atom that has an atomic number of 9, a mass number of 19, and 10 electrons. How many neutrons does this atom have, and what is its charge? What is the isotope name? All right, so let's start with the atomic number. Atomic number of 9 tells us that this is going to be fluorine. So, get my pen ready here. For my symbol, I'm going to put 9 on the bottom for fluorine, and they tell us my mass number is 19. So I can put that up top. For the neutrons, if I do my mass number minus my protons, I will get my neutrons. So I have 10 neutrons in this particular isotope. If I want to find out the charge, the protons minus the electrons give us the charge. So P minus E gives us the charge. Since we have 10 electrons, 9 minus 10 tells us we have a -1 charge. So you can say -1, or actually, even better, most people write charges as 1 minus. Sometimes the minus sign in front is acceptable depending on the context, whether you're saying -1 or 1 minus. Just depends on the situation, which we'll talk about at another point in time. All right, so we've found the neutrons, we've found the charge, we've written the symbol. The isotope name is fluorine. I put my dash, no spaces in between the dash, and then I just put the mass number. And I end up with 19. So fluorine 19 is the isotope name. We have our symbol here, and then we have found our neutrons and our charge. Okay, you're going to do the same thing. Here's a lot of practice set up for you in the You Try It. So sometimes they give you the information you need, and you need to find the things for the empty boxes. So keep in mind that this is a mass number that is given to you in the name. If you know the identity, you can find the atomic number using the periodic table. And then sometimes you have to work backwards to figure out neutrons or protons or charge, etc. Okay? So it's all about using the information we have. Go through and practice this grid, and at the end, you'll be able to check your work. Okay, welcome back. One thing I wanted to discuss before we end this lesson is just some vocabulary on molecules and ions. This vocabulary will prepare us for next time when we talk chemical nomenclature. So we know chemical bonds are forces that hold atoms together. We have ionic and covalent bonds. Ionic bonds are considered electrostatic attractions. So I should add that in here. Ionic is electrostatic attractions, whereas covalent bonds are the sharing of electrons. Since electrostatic attractions require the full transfer of electrons from one atom to another, we're going to represent ionic compounds a bit differently from covalent compounds. A molecule is the term we use for the smallest unit of a compound that retains the chemical characteristics of that compound. Characteristics of the constituent elements are lost. So what that means is by combining carbon and 2 oxygens together, we get a gas in the form of CO2, whereas before, carbon itself is usually a solid and oxygen on its own is usually a gas. Um, when we're looking at structural formulas, those are things like Lewis structures, which you might have done in first year chem. Bonds are shown by lines represented by shared electron pairs. They may not indicate the shape, and we'll get to shapes in a different lesson, but it is good to know the difference between molecular and structural formulas. Molecular formulas just use symbols and subscripts to represent the composition of the molecule. So all of these up here are examples of molecular formulas. If I were to sketch out what these molecules looked like, then I would have a structural formula. Ions, we know, are formed when electrons are lost or gained in ordinary chemical reactions. We end up with a dramatic change in size when electrons are lost or gained, especially if they're lost. If we lose electrons, we're pulling them from the outermost energy level, the valence shell, and essentially we're depleting that valence shell until we get to the shell below it. As a result of removing that outer valence shell, worth of electrons, you end up with fewer energy levels and thus a smaller size. If I'm gaining electrons, I'm completing an energy level, and that can also cause a change in my size. The term cation, it's not cation, it's cation. It refers to a positive charged ion. Usually this refers to metals that have lost electrons to become positively charged. We have anions, which are negatively charged. These are often nonmetals that gain electrons to become negatively charged. Polyatomic ions are also considered anions because these are units of atoms that are usually covalently bonded but behave as one entity and have an overall charge. Typically, it's negative. There is one positive polyatomic ion we'll talk about in the next lesson, but the majority of them are negative, so you can consider them to be anions. Ionic solids is one last vocabulary term because we're talking about ionic compounds in our next lesson. Electrostatic forces hold ions together. The magnitude of that electrostatic attraction can be determined using Coulomb's law. When I say magnitude, I'm talking about the charge. So the greater the charge difference, so if I have a +1 -1 compared to a +2 -2, the electrostatic attractions between a compound that is +2 and -2 are going to be stronger than something with a +1 -1. The magnitude of the charge does impact the strength of the attraction. The reason for this is due to ions being held together tightly and as a result becoming closer together. When they're closer together, they form ionic solids that form this crystal structure like you see with NaCl. And additionally, the Coulombic attraction or Coulombic force becomes greater due to a shorter distance and stronger force. And so these types of compounds end up having high melting points because they have strong intermolecular forces that have to be disrupted. When we look at Coulomb's law, Q is the charge, Q1 and Q2, so the charge of each ion. We have Coulomb constant, which helps us with our units, and then we have the radii, which is the distance between the charges. So when we look at internuclear distance, a shorter internuclear distance results in a greater attraction. All right, that is all for this lesson. Our next lesson will get into the periodic table and chemical nomenclature.